Hello, my name is Benjamin Reichman and I will be presenting our paper, LuNoTim-CT and ConnectionNet, a dataset and baseline for medical image tampering. The motivation for this research stems from three facts that we observed. 1. Medical images are important to diagnosing and treating diseases. 2. Hospitals are vulnerable to cyberattacks, like what happened to the NHS in Britain in 2017 with the WannaCry virus. And 3. Advances in image processing allow for realistic generation of images, including medical images. In this slide, we can see three types of forgeries. On the top, copy-move forgery, which is when one part of an image is moved to hide another part. In the middle, classical inpainting, which is when an algorithm is used to change on a pixel level an image to match the surrounding area of the image. And on the bottom, quite similarly, deep inpainting, which is when a deep neural network does this. How is this related to medical images? Well, these methods could also be applied to medical images. Whereas natural images are rich in texture, color, and have high resolution, most medical images are grayscale and have low resolutions. This makes it a challenge for both humans and algorithms to detect tampered medical images. There has been previous works in detecting traditionally tampered images and GAN-based tampering images, including changing how the first layer of a neural network works, the representation of tampered and untampered images in the latent space. There's also been work in generating fake medical images, particularly what Mirsky et al. Did with CTGAN, where they generated realistic patches of tumor and non-tumor areas of medical images. The main challenge for medical image tampering detection is the lack of large-scale dataset and the lack of advanced algorithms to detect tampered medical images. This research contributes by generating a large-scale dataset with different types of tampering methods, which contains 7,202 tampered CT scans and 300,050 slices. This could serve as the most comprehensive testbed for comparative studies of data security. Additionally, we propose a novel framework, ConnectionNet, to detect tampered medical images. Our dataset contains all three different types of tampering that we introduced earlier on in this presentation: copy-move tampering, classical inpainting tampering, and deep inpainting. We calculate the statistics of nodule size, location, and the number of successive slices a nodule appears in the LIDC IDRI dataset to guide our dataset generation. This lets our generated scans be as realistic as possible. Here are some examples of images from our dataset. The patches outlined in red are generated, and the ones outlined in green are the original patches. And you can see that as we move from copy-move forgery to deep inpainting, they get more and more realistic and thus much more dangerous. This slide shows the statistics of how many tampered scans and slices are contained in our dataset. Here we start looking at the detection branch of our research. We started with a vanilla VGG network, which makes prediction based on high-level features, which are extracted by hierarchical convolution layers. But we saw that we needed the coarse information that are found in the earlier layers when deciding whether a image is tampered or not, and therefore we thought to forward the features from the earlier layers to the decision layer to help out and be able to better make that decision. So first we started by analyzing what the choice of backbone network should be. We started with ResNet and we tried out ResNet 50, 18, and then we tried out VGG and saw that VGG provides the best results. We then trained ConnectionNet with connections at various different stages of VGG on only the deep inpainting portion of the dataset. We then tested the generalizability of our framework by testing the networks that were trained only on the deep inpainting portion of a dataset and testing it on the copy move and the classical inpainting portion of a dataset. And we found that the VGG with the 3 skip connections worked best because it forwarded all the low-level features to the decision layer. We found a few limitations with ConnectionNet. Trained models had more difficulty finding added tumors than removed tumors, with a 13 to 14% lag in identifying added tumors. Most of this lag came from false negatives. In conclusion, in this research, we constructed a dataset of tampered medical images. We generated a dataset that is guided by the statistics of real CT scans. We built a classification network that can detect the tampered CT scans. And this network has been shown to work better when trying to detect removed patches than added patches.